Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family: Susan, Peg, Caitlin, Lynn, and Laura. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener supported and ad-free for everyone, and it's very much appreciated. If you're interested in supporting Boring Books for Bedtime and finding out more about the perks available to subscribers, including exclusive episodes heard nowhere else, you'll find a link to Patreon in the show description. You'll also find a link to buymeacoffee.com, where you can support us with a one-time tip, no subscription required. I hope you'll take a moment to check them out. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight we're relaxing with more from one of my favorite books, Astronomy for Young Folks by Isabel Martin Lewis, A.M., connected with the Nautical Almanac Office of the U.S. Naval Observatory, and published in 1922 by Duffield and Company, New York. Let's pick up right where we left off, in the middle of Chapter 21, Is the Moon a Dead World? Let's begin. Geologists tell us that more oxygen is to be found in the first 6 feet of the Earth's crust than in all of the atmosphere above. Does oxygen not exist in the surface rocks of the moon as well? Volcanic action, we are told, is primarily an escape of gases from the interior, chiefly hydrogen, nitrogen, hydrocarbons, sulfur, and various compounds, as well as vast quantities of steam. Beneath the surface, chemical change is continually taking place, which results in the release of an enormous amount of heat. Some of the gases mentioned above combine with the oxygen in the surface rocks, and heat is evolved. It is a known fact that there is great inherent heat in the Earth's surface crust. Why not in the moon's surface crust as well? The water that would be expelled in the form of steam from volcanic vents on the moon would be transformed immediately into hoarfrost, snow, and ice, and would settle down upon the flanks of the crater cones or vents. It should be borne in mind that only volcanic activity on an enormous scale would be plainly visible to us, even with the powerful telescopes at our command. Ordinary eruptions such as occur on our own planet would be very difficult to detect, since the escaping vapors would rapidly pass into the solid state and settle down upon the flanks of the crater cones or vents. We would observe in general little if any change in an object, unless we chance to be looking at it at the time of the eruption, when it might appear to be temporarily obscured by a veil of vapors. What are the chances that we would be carefully observing at the precise time of an eruption a minute marking 2 or 3 miles in diameter on a surface as large as all of North America, a surface that is covered with some 30,000 charted craters, numberless crater pits, streaks, rays, spots, clefts, and rills in intricate systems, mountain chains and valleys, and a mass of intricate detail? If we were looking at the Earth from the moon with the aid of a powerful telescope, would we be apt to notice an eruption of Vesuvius, or Katmai, or Mauna Loa. Objects 4 or 5 miles in diameter would appear as hazy spots, with nothing distinctive or remarkable in their appearance. Yet vapor and steam arising from terrestrial volcanoes would be carried by our atmosphere over an area of many square miles, while there is no atmosphere on the moon to spread the vapors that may arise from similar volcanic vents. It would have to be a cataclysmic change indeed to be accepted as indisputable evidence that change is taking place on the moon, and the days of gigantic upheavals are probably over on our satellite as well as on the Earth. If volcanic activity is still taking place on the moon, it is probably in a mild form, such as a comparatively quiet emission of gases from volcanic vents and fumaroles. Such forms of activity would not be plainly visible at this distance, even with the aid of powerful telescopes. The problem of detecting changes on the moon is complicated by the fact that a change of illumination greatly alters the appearance of all lunar markings. Such a change is continually taking place in the course of the month. A marking that stands out in bold relief at lunar sunrise or sunset will change entirely in appearance a few days later under a high sun, or even disappear from view entirely. These changes in phase or illumination have to be taken account of in the search for evidence of actual change. To decide whether or not change has actually taken place, the object must be viewed under similar conditions, so far as they can be obtained. Even when special care is taken in this respect, the suspected evidence of change is usually explained away as due to differences in illumination or seeing by those who have not observed the object themselves and are not in sympathy with the view that the moon is anything but a dead world. As regards the question of life on the moon, it is interesting to consider the facts brought out by investigations made by scientists connected with the geophysical laboratory of the Carnegie Institute in the Valley of 10,000 Smokes. The volcanic activity there takes the form of eruptions from numerous small vents or fumaroles, and 99% of the emanations are water vapor. It was observed that blue-green algae were living at the edge of active vents, emitting ammonia compounds at a temperature of 212 degrees Fahrenheit. They were not found, however, near vents from which ammonia compounds were not being emitted. If life exists under such conditions, it is conceivable that suitable conditions for the support of certain forms of life, animal as well as vegetable, may be found in low-lying valleys and crevices and upon the floors of craters, where certain gases essential to the support of life might be evolved from many small volcanic vents and fumaroles. Many theories have been advanced to explain the origin of the lunar craters, which have no counterpart on our own planet. They are saucer-like depressions in the surface of the moon, frequently of such great size that an observer standing in the center would not be able to see either side of the crater owing to the curvature of the moon's surface. Craters 50, 60, or 100 miles in diameter are by no means uncommon, while there are thousands between 5 and 50 miles in diameter. A characteristic feature of many craters is a central peak, and the surrounding walls are often a mile or more high, and in some instances are symmetrically terraced. New craters have been formed on the sides or floors of old craters, and these are always more clear-cut and sharper in outlines than the old formations, and generally much smaller. A number of craters are surrounded by a system of light streaks or rays of unknown origin that extend in some instances to enormous distances on all sides of the crater. The most conspicuous system is the one surrounding the lunar crater Tycho near the south pole of the Moon. The rays originating in this crater extend in all directions for hundreds of miles, without turning aside for any obstructions, passing over mountains, craters, and plains in their course, in practically straight lines like spokes in a wheel. This ray system of Tycho is the most noticeable marking on the Moon's surface at the time of full moon. As these streaks cast no shadow, they are apparently cracks in the surface that have filled up with some light-colored material from below. Their origin has never been satisfactorily explained. As to the origin of the lunar craters, some believe that they were produced in past ages by a bombardment of the lunar surface by huge meteoric masses, but there are many objections to this theory that we will not take up here. It is more generally believed that the lunar craters are a result of volcanic activity on an enormous scale which took place on the Moon many ages ago and which has now practically ceased, its only manifestations now taking the form of a quiet emission of gases from small volcanic vents or fumaroles which exist all over the lunar surface, but which are to be found in greatest numbers on the floors and sides of craters. Chapter 22. Comets. The orbits of comets are inclined at all angles to each other and to the orbits of the planets, which, on the other hand, lie very nearly in the same plane. The larger members of the Sun's family, the planets and their satellites, revolve from west to east around the Sun. Comets, on the contrary, frequently retrograde or back around the Sun in the opposite direction, from east to west. The paths that these erratic visitors follow in their journeys around the Sun bear not the slightest resemblance to the paths of the planets, which are almost perfect circles. The orbits of comets are ellipses that are greatly elongated, or parabolas. If the orbit is a parabola, the comet makes one and only one visit to the Sun, coming from interstellar space and returning thereto after a brief sojourn within our solar system. Donati's comet of 1858, one of the greatest comets of the 19th century, has a period of more than 2,000 years, and its aphelion, the point in its orbit farthest away from the Sun, was 5 times more distant than the orbit of Neptune. There is, however, a class of comets known as periodic comets that have extremely short periods of revolution around the Sun. To this class belongs Halley's comet, whose period of 75 years exceeds that of any other short-period comet. Encke's comet, on the other hand, has a period of 3 1/3 years, which is the shortest cometary period known. Most of the periodic comets are inconspicuous and only visible telescopically, even when comparatively near to the Earth. Halley's comet is the only one of this class that lays any pretensions to remarkable size or brilliancy, and it also is showing the effects of disintegration resulting from too frequent visits to the Sun. Comets are bodies of great bulk or volume and small total mass. Their tails, which only develop in the vicinity of the Sun, are formed of the rarest gases, and the best vacuum that man can produce would not be in as tenuous a state as the material existing in the tails of comets. There are many proofs of the extreme tenuity of comets. The Earth has on a number of occasions passed directly through the tails of comets without experiencing the slightest visible effects. Stars shine undimmed in luster even through the heads of comets. If the Earth should encounter a comet head-on, it is doubtful it would experience anything more serious than a shower of meteors, which would be consumed by friction with the Earth's atmosphere, or a fall of meteorites over a small area of a few square miles. It is possible, however, that matter in the nucleus, the star-like condensation in the head of a comet, may consist of individual particles weighing in some instances a number of tons, surrounded by a gaseous envelope and held together by the loose bonds of their mutual attraction. If the Earth should encounter the nucleus of a comet, considerable damage might be done over a portion of the Earth's surface, but the chances of such an occurrence are less than 1 in a million. Since the total mass of a comet is so small, a close approach to one of the planets, especially Jupiter, produces great changes in the form of the comet's orbit, though the motion of the planet is not disturbed in the slightest degree by the encounter. The majority of all the short-period comets have been captured by Jupiter. That is, the original orbits have been so changed by the perturbations produced by close approaches to the giant planet that their aphelia, or the points in their orbits farthest from the Sun, lie in the vicinity of Jupiter's orbit. Several of the other planets have also captured comets in this sense, and the fact that the aphelia of a number of comets are grouped at certain definite intervals beyond the orbit of Neptune has been considered by some astronomers to be an indication that there are 2 or more additional planets in the solar system revolving around the Sun at these distances. The most interesting feature of a comet is its characteristic tail, which develops and increases in size and brilliance as the comet approaches the Sun. As the tail is always turned away from the Sun, it follows the comet as it draws near the Sun and precedes it as it departs. Its origin is due, it is believed, both to electrical repulsion and light pressure acting upon minute particles of matter in the coma or head of the comet. The curvature of the tail depends upon the nature of the gases of which it is composed. Long, straight tails consist chiefly of hydrogen, curved tails of hydrocarbons, and short, bushy tails of mixtures of iron, sodium, and other metallic vapors. At times, the same comet will have 2 or more tails of different types. Since the material driven off from the nucleus or head of a comet by electrical repulsion and light pressure is never recovered, it is evident that comets are continually disintegrating. Also, comets that have passed close to the Sun at perihelion have frequently been so disrupted by tidal forces that one nucleus has separated into several parts, and the newly formed nuclei have pursued paths parallel to the original orbit, each nucleus developing a tail of its own. Many periodic comets, it is now known, have gradually been broken up and dissipated into periodic swarms of meteors as a result of the disruptive effect produced by too frequent returns to the vicinity of the Sun. These swarms of meteors continue to travel around the Sun in the orbits of their former comets. The Earth encounters a number of such swarms every year at certain definite times. The largest and best known of these swarms or showers are the Leonids, which appear about November 15th, the Andromedas or Biolids, which appear later in the same month, and the Perseids, which appear early in August. The swarms are named for the constellations in which their radiant lies, that is, the point in the heavens from which they appear to radiate. The position of the radiant depends upon the direction from which the swarm is coming. It is simply a matter of perspective that the individual particles appear to radiate from the one point, for they are actually traveling in parallel lines. The luminosity of these meteoric particles is caused by the friction produced by their passage through the atmosphere. They always appear noiselessly because they are mere particles of meteoric dust, weighing at the most scarcely a grain. They differ greatly in this respect from their large and noisy relatives, the meteorites, bolides, and fireballs. Numberless small meteoric particles are entrapped by the Earth's atmosphere every day. They are referred to as shooting stars or falling stars, though of course they are not in any sense stars. It is only when these meteoric particles travel in well-defined cometary orbits and appear at certain definite times every year that they are referred to as swarms or showers of meteors. The luminosity of comets is due not only to reflected sunlight, but to certain unknown causes that produce sudden or erratic increases or decreases of brilliancy. The causes of these sudden changes in luminosity are unknown. Possibly electrical discharges or chance collisions between fragments of considerable size may account for some of them. The peculiar behavior of the tails of comets at certain times has frequently been noted and suggests the existence of quantities of finely divided meteoric or gaseous matter within the solar system that has no appreciable effect upon the huge planetary masses, but offers sensible resistance to the passage of the tenuous gases of which the tails of comets are composed. The fact that the Earth daily encounters meteoric dust, meteorites, and fireballs also indicates that meteoric matter exists in considerable quantities within our solar system. Tails of comets appear at times to be twisted or brushed aside as if they had encountered some unknown force or some resisting medium. Up to the present time, several hundred comets have been discovered. Nearly 3/4 of this number travel in orbits that appear to be parabolas. Of the remaining number, there are about 40 that have been captured by the major planets, Jupiter, Saturn, Uranus, and Neptune, though Jupiter possesses the lion's share of these captured comets. Scarcely a year passes by that several comets are not discovered. Most of these are telescopic, however, even when they are near the sun and at their greatest brilliancy. Naked eye comets of great splendor and brilliancy are comparatively rare, and there has been a particular dearth of such unusual comets during the past 30 years or so. The last spectacular comet, unless we make an exception of Halley's periodic comet, which made its return according to prediction in 1910, was the great comet of 1882, which was visible in broad daylight close to the sun, and at its perihelion passage swept through the solar corona with a velocity that exceeded 250 miles a second and carried it through 180 degrees of its orbit in less than 3 hours. such comets approach much closer to the Sun than others. The majority of all comets observed have come within the Earth's orbit, and no known comet has its perihelion beyond the orbit of Jupiter. It is, of course, possible that there may be a number of comets that never come within the orbit of Jupiter, but it is very unlikely that any such comet would ever be discovered. The majority of comets are simply small, fuzzy points of light that are only visible telescopically, and the greater the perihelion distance of the comet, the less likely is it to be seen with the naked eye. Since comets as well as planets obey Kepler's first law, known as the law of areas, and sweep over equal areas in equal times, it is evident that when a comet is at perihelion or nearest to the Sun, it is moving at maximum speed, and when it is at aphelion or farthest from the Sun, it is moving at minimum speed. Moreover, its speed at these 2 points in its orbit varies tremendously, since the orbits of comets are ellipses of very high eccentricity. The speed with which the planets are traveling is, on the other hand, remarkably uniform, since their orbits are nearly circular. The leisurely speed with which a comet travels through the frigid outer regions of the solar system is gradually accelerated as the comet draws nearer and nearer to the Sun, until it has acquired near the time of perihelion passage a velocity that occasionally exceeds 200 miles a second. Here also, the great increase in light and heat and the strong magnetic field of the Sun produce complex changes in the gaseous and meteoric substances of which the comet is composed, until the characteristic tail and peculiar cometary features are fully developed. As the comet again recedes from the Sun after perihelion passage, its speed slackens once more. It soon parts with its tail and other spectacular features and fades rapidly from view, even in the largest telescopes. Chapter 23. Meteorites. Meteorites, bolides or fireballs, as they are variously called, are stones that fall to the earth from the heavens. They furnish the one tangible evidence that we possess, aside from that furnished by the spectroscope, as to the composition of other bodies in space, and it is a significant fact that no unknown elements have ever been found in meteorites, though the forms in which they appear are so characteristic that they make these stones readily distinguishable from stones of terrestrial origin. The origin of meteorites is not definitely known, but the evidence is very strong in favor of the theory that they are the larger fragments of disintegrated comets, of which meteors and shooting stars are the smaller, the distinction between the two being simply that the latter class includes all bodies that are completely consumed by friction with the Earth's atmosphere and therefore only reach the surface in the form of meteoric dust. According to other theories, meteorites may be fragments of shattered worlds that have chanced to come too near to a larger body and have been disrupted, or they may possibly be the larger fragments of the disintegrated comets, of which the meteoric swarms are the smaller. Interplanetary space is not altogether a void. Our own planet sweeps up in the course of a single day, it has been estimated, approximately 20 million shooting stars or meteors of sufficient size to be visible to the naked eye, while the estimate for the telescopic particles runs up to 400 million. Meteorites, on the other hand, are comparatively rare. On the average, it has been estimated about 100 meteorites strike the Earth in the course of a year, of which number only 2 or 3 are actually seen. According to Bulletin 94 of the U.S. National Museum, approximately 650 falls and finds of meteorites have been reported, representatives of which appear in museums and private collections. Meteorites, as well as shooting stars and meteors, frequently appear in showers. In such instances, the fall usually consists of several hundred or thousand individual stones, and the area over which they fall is several square miles in extent and roughly ellipsoidal in shape. In one of the most remarkable of such falls, 100,000 stones, varying in weight from 15 pounds to a small fraction of an ounce, fell near Pultusk, Poland. Another remarkable fall of meteorites occurred at L'Aigle, France in 1803. Between 2,000 and 3,000 stones fell over an ellipsoidal area of 6 2/10 miles in greatest diameter, the aggregate weight of the stones being not less than 75 pounds. This fall of stones is of particular interest, since it took place at a time when men were still very doubtful as to whether or not stones actually fell to earth from the heavens. After this fall had occurred in a most populous district of France in broad daylight, and attended by violent explosions that lasted for 5 or 6 minutes, and were heard for a distance of 75 miles, no reasonable doubt could longer be held as to the actuality of such phenomena. Meteorites are without exception of an igneous nature. That is, they are rocks that have solidified from a molten condition. They can be classified into 3 groups: aerolites or stony meteorites, sideralites or stony iron meteorites, and siderites or iron meteorites. More iron meteorites seem to have fallen in Mexico and Greenland than in any other part of the world, at least of its land surface. Yet, strange to say, of all the meteorites that have been seen to fall, only 9 belong to the group of siderites or iron meteorites. Though the 3 largest meteorites known, Parry's meteorite from Cape York, Greenland, weighing 37 1/2 tons, the meteorite lying on the plain near Bacabarito, Mexico, weighing about 20 tons, and the Willamette, Oregon meteorite, weighing 15 1/2 tons, all belong to this group. Moreover, all the Canyon Diablo meteorites, which are strewn concentrically around Coon Mountain crater in northern Arizona to a distance of about 5 miles, are members of this same group. Coon Mountain or Meteor Crater itself is a perfectly round hole, about 600 feet deep and over 4,000 feet in diameter, and was formed, it is believed, by the impact of a huge meteorite which has never been found. It is believed that the Canyon Diablo meteorites, of which there are nearly 400 individuals in the U.S. National Museum alone, were all members of this same fall. It is possible that these meteorites of the Canyon Diablo district, with the huge meteorite that produced the crater itself, formed the nucleus of a comet that struck the Earth not more than 5,000 years ago, according to the geological evidence. All iron meteorites or siderites, from the Greek sideros, iron, are composed chiefly of alloys of nickel and iron. The percentage of nickel in these iron meteorites is very small, usually from 5 to 10%, while the iron forms about 90 or 95% of the whole. Cobalt is also present in practically all iron meteorites, in small quantities of 1% or less. Usually small quantities of iron sulfide and phosphide, as well as graphite or some other form of carbon, appear in the iron meteorites, and in some instances black and white diamonds have been found, as in some of the Canyon Diablo irons. A very interesting and beautiful feature of many iron meteorites is the Widmanstätten figures, which appear when a section of such a stone is polished and treated by means of a weak acid. These figures are due to the unequal solubility of the 3 different alloys of nickel and iron of which the stones are composed. The irons giving the Widmanstätten figures are known as octahedral irons. Other irons, known as hexahedral irons, give figures of a different type known as Neumann figures when the polished section is treated with weak acid, while other irons are so homogeneous in their composition that they show no figures at all. Aerolites or stony meteorites occur more abundantly than iron or stony iron types, and they are classified into many divisions and subdivisions according to their composition. In these stones appear certain compounds that are commonly met with in terrestrial igneous rocks. The mineral that is most abundant in the stony meteorites, composing sometimes nearly 75% of the stone, is a magnesium and iron silicate known as olivine, which is also usually present in terrestrial rocks of an igneous nature. Certain compounds found in the stony meteorites are rarely if ever found in terrestrial rocks, however, and these serve to distinguish the stony meteorites readily from stones of terrestrial origin. The alloys of iron and nickel, for instance, that occur in minor quantities in the stony meteorites and make up usually about 95% of the mass of the iron meteorites, are never found in terrestrial rocks. Although about 30 of the terrestrial elements are to be found in meteorites, the forms and compounds in which they appear are so characteristic and on the whole so different from those occurring in terrestrial rocks that the analyst has no difficulty in distinguishing between the two. There are, for instance, certain formations known as chondrules, peculiar spherical and oval shapes, varying in size from minute particles to objects the size of walnuts, appearing in many varieties of stony meteorites that are never found in terrestrial rocks, and that are one of the most puzzling features associated with the origin and nature of these stones. Sometimes the chondrules are so loosely embedded in the stone that they fall away when it is broken. In some instances, almost the entire stone is made up of these chondrules. According to one theory, the chondrules were originally molten drops, like fiery rain, and their internal structure, which is greatly varied, depends upon their conditions of cooling. Stony meteorites in which these chondrules are to be found are spoken of as chondrites. There are white and gray and black chondrites, and crystalline and carbonaceous chondrites, according to the nature of the chondrules found in the stones. Stony meteorites also contain minute quantities of iron and nickel alloys in the form of drops or stringers. Upon entering the Earth's atmosphere, stony meteorites become coated with a thin black crust, which is a glass formed by the fusion of its surface materials, by the heat generated during its passage through the atmosphere. In many of the stony meteorites, there also appear fine thread-like veins, which are due to the fracturing of the stone prior to its entrance into the atmosphere. The material filling these veins is coal-black in color, opaque, and of an unknown composition. Many meteorites show signs of collisions and encounters with other meteorites outside of the atmosphere, as would be expected as they travel in swarms and groups. Sometimes the entire meteorite is composed of fragments of two or more distinct stones cemented together. Such a stone is spoken of as a breccia. In the third class of meteorites to which we now come, known as the stony iron meteorites, there is a network or sponge of nickel-iron alloy, the interstices of which are filled with stony material. When this network or sponge is continuous, the meteorite is spoken of as a stony iron palisite. When the network of metal is more or less disconnected, the meteorite is a mesosiderite. If meteorites are heated in a vacuum, the conditions existing in interplanetary space being thus produced to a certain extent, they give forth their occluded gases, and it has been found that these gases give spectra identical with the spectra of certain comets. Meteoric irons give forth hydrogen as their characteristic gas, while the gases occluded in the stony meteorites are chiefly the oxides of carbon, carbon monoxide, and carbon dioxide. It has been found that the amount of gases contained in a large meteorite or shower of meteorites is sufficient to form the tail of a comet. These facts all tend to strengthen the belief that meteorites are indeed cometary fragments. In view of the fact that some geologists believe meteorites may be fragments of other worlds, it is of interest to know that so far no fossil-bearing meteorites have been found, and if meteorites are fragments of a shattered world, such worlds must have been reduced to a molten condition at the time of the catastrophe. The rapid passage of the meteorite through the air leaves a partial vacuum in its trail, into which rush the molecules of air from all sides, producing the characteristic noises that accompany the passage of a meteorite, which have been variously compared to the rattle of artillery, the distant booming of cannons, or the rumble of thunder. There may be also explosions of inflammable gases occluded in the crevices of the meteorite, which will shatter it into fragments, or the meteorite may be shattered by the resistance and pressure of the atmosphere, or as a result of the extremes of temperature existing between the interior and its surface. Many meteorites have actually been seen to burst into fragments in the air with a loud report. There is practically no foundation for the belief that germs of life have been brought to our planet on such igneous rocks. No microscopic examinations of meteorites have yielded any results that could be interpreted in favor of such a view. Falls of meteorites are accompanied in nearly every instance by terrific explosions and sharp reports that can be heard for many miles around, often causing the ground to shake as in an earthquake. The meteorite itself has been described as resembling a ball of fire or the headlight of a locomotive, and is followed frequently by a trail of light or a cloud of smoke. At the time it enters our atmosphere, a meteorite is moving with planetary velocity, ranging from 2 to 45 miles per second. Its interior is intensely cold, approaching in temperature the absolute zero of interplanetary space, and it is therefore far more brittle than it would be at ordinary temperatures. As it plows its way into the Earth's atmosphere, its surface temperature is soon raised by friction to at least 3,000 or 4,000 degrees Celsius, which is sufficient to fuse all surface materials into the characteristic black crust with which stony meteorites are coated. Meteorites are usually first seen at an altitude of 50 or 60 miles, although they are moving with a velocity comparable to that of the planets when they enter the Earth's atmosphere. This velocity is so rapidly reduced by friction with the atmosphere that they usually drop to the surface of the Earth with a velocity about equal to that of ordinary falling objects. The flight of a meteorite often extends over a path several hundred miles in length, and the meteorite may be seen by many observers in several different states, and yet finally fall in some unknown spot and never be found. The evidence gathered regarding the actual fall of meteorites is often contradictory. Some stones are too hot to handle for hours after they fall. Others are merely warm, while still others have been picked up cool or even intensely cold. Meteorites have been seen to fall upon dried grass and upon straw without producing even charring effects. The evidence regarding the depths to which meteorites penetrate the ground is quite as conflicting. The largest of all the stony meteorites which fell at Kőrnyegénye, Hungary, weighed 647 pounds and buried itself to a depth of 11 feet. Yet Parry's Cape York iron meteorite, weighing 37½ tons, was only partially covered and showed no signs of abrasions of surface resulting from the fall. The Willamette iron meteorite, weighing 16½ tons, lay in a forest when found and was not deeply buried. The Bakuberito iron meteorite, weighing 20 tons, lay in soft soil barely beneath the level of the surface. On the other hand, a fragment of a stony iron meteorite weighing 437 pounds that fell at Esterville, Iowa, buried itself 8 feet in stiff clay. Geologists in charge of the meteoric collections at various museums quite frequently have stones sent to them for analysis that are reputed to be of celestial origin. More often than not, such stones are found to be purely terrestrial in their origin. The composition of a meteorite is so characteristic and unique that such a stone can never be mistaken. Finds of bona fide meteorites are, on the whole, extremely rare. It is also a peculiar fact that meteorites are usually observed in the months when ordinary meteors or periodic swarms of meteors are least prevalent, that is, in the months of May, June, and July. And with that conclusion to Chapter 23, I think we'll end this evening's reading from Astronomy for Young Folks, a book which never fails to teach me something. I hope you enjoyed it as well. If you'd like to read this work for yourself, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.